What is temperature? And what is the difference between traditional, thermodynamic, and Kelvin temperature scales? We're going to look into answering these questions and finding connections in the theory of thermodynamics. If we're going to get anywhere looking at heat, we need a good understanding of temperature. The problem is, it is quite a challenging thing to really pin down. You might have an understanding that temperature is a measure of the average kinetic energy of the particles in a body. If so, well done, because that is a really good way of thinking about it. It is flawed though. For one thing, temperature has units of degrees Celsius or Kelvin, which are not units for energy. So how can temperature be a measure of kinetic energy? Let's dig a little deeper so that we can be more confident as we investigate thermodynamics. Temperature is a measure of the average kinetic energy of the particles in a body. I do like that definition and we are pretty much going to stick with it, but hopefully we'll get to understand what it really means a bit more. Let's start with units. Let's start with degrees Fahrenheit. The Fahrenheit scale was a brilliant idea that relates temperature to the human body. It has the freezing point of water as 32 degrees Fahrenheit and human body temperature at 100 degrees Fahrenheit. That's a great idea, but not really very good for serious science since human body temperature changes. The Celsius scale improved on this by setting 0 degrees C as the freezing point of water and 100 degrees C as the boiling point of water. Nice easy numbers, and water can easily be frozen or boiled. There's a couple of problems though. One is that it depends on water and scientists don't like depending on a material because that material could change. Going further on that, you should never really trust a unit with degrees in the name. Using the word degrees suggests you are just comparing your result to something else. It is not absolute. It could change if that other thing changed. So there is the Kelvin scale. When it first appeared, it was written as degrees Kelvin, but as it is an absolute scale, the degrees were dropped. I've mentioned absolute twice now, but what do I mean? Well, the Kelvin scale is built upon the thermodynamic temperature scale, and the thermodynamic temperature scale is an amazing thing because it has absolute zero. That means it is an absolute scale. Absolute zero is often thought of as the temperature when everything stops moving, but that's not quite true. Remember, we are interested in three types of kinetic energy: translational, vibrational, and rotational. Absolute zero is when these reach their minimum possible values, which is also when the internal energy reaches its minimum possible value. U becomes its lowest possible. So, a hydrogen atom that is in its lowest energy state is at absolute zero. A water molecule that is in its lowest energy state is at absolute zero. A long-chain hydrocarbon molecule that is in its lowest energy state is at absolute zero. This is the third law of thermodynamics, that absolute zero exists. Absolute zero does not depend on anything. It is defined by being the lowest possible energy state. And that is why it is absolute. And that's great, because it means we can have a fixed point that is not dependent on some other material. we can work from there with more kinetic energy, meaning there is a higher temperature. We're saying here that we want to measure the concept of temperature using kinetic energy. That's nice, but not particularly useful as it is really hard to measure. Instead, William Thomson, 1st Baron Kelvin, also known as Lord Kelvin, had the idea of using absolute zero as the lower fixed point and the triple point of water as the upper fixed point. The triple point of water is the temperature when all three phases of water are in equilibrium. So that means liquid, solid, and gas are all present at the same time. This happens at 0.01 degrees Celsius, so that is the upper fixed point. For convenience, since everyone was already using degrees C, the upper fixed point was defined as being exactly 273.16 Kelvin. This is slightly above the melting point of water in 1 atmosphere of pressure, which is 273.15 Kelvin. We started with a definition of temperature that it is a measure of the average kinetic energy of the particles in a body, and, to be honest, that's where we've ended up still. Hopefully though you have a better understanding of what we mean by kinetic energy and why that is a decent definition. So we have the thermodynamic temperature that does not depend on anything. This is superb, but difficult to use. Then we have the Kelvin scale that does depend on the triple point of water. Then we have the Celsius scale that depends on both the melting point and the boiling point of water. Each is getting more convenient, but still, how do we measure it? How do we make use of these scales? How can we get measurements that will allow us, as engineers, to see the flow of heat in a complex machine such as a steam engine? Let's look at that in the next lesson video.